Let's get ready to do some math! All right, folks, Berto coming at you with another advanced placement calculus review lesson. Video review lesson. Today is Wednesday, even though I'm making this video on Monday, but Wednesday is when you'll be seeing it. I hope you've tried that AP demo, okay, as far as uploading stuff, and took a video that I put up there, took a look at that video. Make sure you know what's going on the day of the AP exam. I don't want you having to deal with nonsense with uploading stuff, okay? Make sure you've actually practiced it. Let's dive into some more miscellaneous types of problems. Thursday and Friday, the next 2 days, we'll focus on types of problems they put on AP Classroom, okay, which I think might be like a wink-wink that they're going to be on the AP, but we don't know that for sure. So let's dive in here. This 2010 problem, let's get some more filth going on. We'll do this 2010 problem right here. It's filthy. And this 2007 problem, not all of it is filthy, but some is filthy. Just like this one, not all of it is filthy, but some is filthy. I want you guys to get used to what you're going to see, okay? You're going to see problems where you could do a couple parts, and other parts you're going to be like, what in good heck is this, okay? You're just going to have to do the best you can to earn points. Skip something you can't do. Do all the... Look, if you could do part A and part B is impossible, don't be like, well, I can't do part C. Forget it. No, move on to part C. You'd be surprised. Sometimes it's pretty doable. Do everything you can, then come back, okay? Make sure you have enough time to submit. They give you that 5 minutes to submit right there. Make sure that you're actually putting in your work on how to submit your answers, okay? More on that. We'll keep talking about it, but make sure you take a look at that demo, right? It shouldn't be too terrible to do. So this one here, the 2010 AP, was a horrible AP, okay? It was a really rough part 2. And this problem, A and B are good, and then part C kind of deteriorates into madness. Number 5, the function g is defined in differentiable. Okay, so differentiable we know is important. On the closed interval, -7 to 5. Satisfies little niche condition. G of 0 is 5. They don't give you the graph of g. They give you the graph of g prime, which is the derivative of g. And we got a semicircle and 3 line segments as shown in the figure above. It's another graph of the derivative problem. We've done a bunch of these. You've had them on take-homes as well. They're kind of pushing a little bit accumulation function as far as what you're going to see in the next 2 videos. For Thursday and Friday, we'll do some accumulation function. Very similar to these problems right here. I just figured let's do those a little bit later in the week so they're a little bit more fresh in your mind. But it's almost the same as these problems right here. Part A, which is a part A, they want g of 3 and they want g of -2. I'm telling you right now, they're going to have this on your AP exam somewhere. This is the fundamental theorem. If you want a function evaluated at an x value, as long as you know the function evaluated at some other x value and the rate at which the function changes, you'll be able to get the function evaluated at any x value you want. Remember, we know what g of 0 is. We want to know what the heck was the change in g from 0 to 3. So if you want the change in g, you integrate the rate at which g changes, okay? Just like if they don't have integrate the rate, the applied problems on the AP, this is still technically integrate the rate. That's why, people aren't sure if those are going to show up or not, but this is definitely fair game right here. G of 0 we know is equal to 5, plus the integral from 0 to 3 of g prime of x. It's annoying because the integral from 0 to 2 is one shape, and then you have to go from 2 to 3, this other shape right here. But no, it's going to be positive, right? You're integrating forward the regions above. This is a right triangle. His base is 1, his height is 3, so 1/2 times 1 times 3 is going to be 3/2. That's his area. This guy from 0 to 2, it's a quarter circle. Quarter circles freak people out. Okay, remember a quarter circle, the area of a circle is pi r squared, right? So the area of a quarter circle, 1/4 pi r squared. It's really not too terrible. We know the radius is 2 right here, so it's really 1/4 pi times 2 squared. And that's really just pi, right? 1/4 times 4. So this area right here is pi. So the integral is really going to be pi plus 3 over 2, right? So pi plus 3 over 2. Simplify it if you want to. No, don't simplify it. Stick it to the squirrels, okay? You make a mistake simplifying it, you're going to lose points. I don't want you to lose those points. Now we have to actually do g of -2. Same type of thing. I can't tell you how many people are going to be taking the AP exam who have no idea how to do this, by the way. Okay, so we'll start with g of 0. Technically, you could start with g of 3 if you want. It makes the problem more complicated, and if you flub this up, then you could end up, well, not getting it wrong. If you use the correct answer appropriately, it'll still give you points. But use what they give you. It's always safer to use what they give you than what you got. Integral from 0 to -2 now of g prime of x with respect to x. We know g of 0 is equal to 5. No problems there. Plus, integral from 0 to -2. That means we're going from here to here. Okay, 0 to -2. Integrating backward the regions above, okay? If you integrate backward in the regions above, that's going to be negative right there. So we know it's going to be a negative right here, and it's just the negative of what this area is right here. And we already know this area is pi. It's just the quarter circle. It's the same as this one, so it's really negative pi. That's the integral, and whoop, There it is. Okay, so actually pretty easy to do that right there. Should be pretty dang doable. That right there will get you 3 points. Okay, pretty big. Part B, piece of cake. Find the x-coordinate of each point of inflection for the graph of y equals g of x, the interval -7 to 5. Explain your reasoning. Point of inflection, well, surely there must be some sort of test. Okay, and if you want to know where G has a point of inflection, you want to draw the G double prime line. But I'm not giving the graph of G double prime. I'm giving the graph of G prime. You telling me I want to draw the line for the derivative of the graph that we're given? That's when you check. Very good. Increasing and decreasing slope, okay? You can see that this thing starts out increasing. Right here at -2, the slope doesn't exist. But after -2, the slope is still positive. It's still increasing. So you can say it increases from -7 all the way to 0. All right, there's nothing wrong with that right there. If you want to say it increases from -7 to -2, then again from -2 to 0, be my guess. It's not going to be a point of inflection anyway. There's not going to be a sign change. Then we can see it decreases from 0 to 2. Then you have a positive slope from 2 to 3. And then a negative slope from 3 to 5. Okay, so it looks a little something like that, my G double prime line. So now we know where the inflection points are. So inflection points at x equals, and we know it's 0, 2, 3. It's just the justification that bothers people. You got to justify in terms of the graph that you're given. If your justification does not have G prime in there, you're in trouble. Okay, you could also say the slope of G if you want, but G prime would be fine. It's the better way to go. What happens at 0, 2, and 3? What happens to the graph of G prime at 0? Oh, it changed from increasing to decreasing. What happens to the graph at G prime at 2? Oh, it changed from decreasing to increasing. What happens to the graph at G prime at 3? Oh, it changed from increasing to decreasing. That's your justification, because G prime changes from increasing to decreasing, or vice versa, vice versa. We've done this a lot, okay? You know, sometimes these things change, these justifications. Usually, they're kind of the traditional type of problem, okay? But make sure you justify in terms of what you're given. You were given G prime. That's how I knew, you know, people want to say G double prime changes sign, right? G double prime changes sign. Well, how'd you know G double prime changes sign, okay? Because you saw the slope of G prime change sign. Slope of G prime changes signs. And if you want, by the way, you could use this justification instead of this justification, because if the slope of G prime does change signs, okay, that means that G prime is either change from increasing to decreasing or decreasing to increasing, because its slope is either changing from positive to negative or negative to positive. So this works out fine as well, okay? I think this one's a little bit easier. It's the one that's always on the AP answer key. But regardless, do what you will. And now, how many points could we earn in part C? Because this is worth 4 points, okay? So you actually get 5 points. 5 points for that right there. That's money. That's lit, okay? That's really good. If you want to be, you know, a 5, you should be able to pick up another point of 2 here. I think a lot of you guys could pick up another point of 2 here. Let the function h be defined by h of x equals g of x minus 1/2 x squared. So it involves this fictional function g that they talked about. They only give us the derivative for. Then they want the x-coordinate of each critical point of h. From -7 to 5. And then they want to classify each critical point as either being a relative minimum, relative maximum, or neither. Okay, and remember a critical point for a function, that's going to be where the function's derivative equals 0 or where the function's derivative does not exist. Okay, so that's what we're looking for, right? Where h prime equals 0, h prime does not exist. And if they're talking about a critical point, remember, you could have relative maxes, relative mins, or neither. You know, if it's a critical point where h prime is equal to 0, then it's easy to see the relative max, relative min. But don't forget about the neither, this type of thing right here. But this still works even if it's not a horizontal tangent line. You could still have a relative min. You could still have a relative max. Maybe it looks a little something like that. As far as the neither, I mean, you could still be increasing and decreasing at a increasing at a sharp point. Maybe it does something like this and then something like that. Okay, you know, it's kind of hard to see. We don't normally talk about things like that. But let's dive right in, because they give us h of x. So what is that? G of x minus 1/2 x squared. We want to know where the derivative of this is equal to 0 undefined. So let's get the derivative, right? H prime of x. Derivative g of x. If you can't do that, slacker. It's g prime of x. Come on. Can break up derivatives over subtraction. Minus 2 times 1/2 is 1. X to the 1 less. It's just g prime of x minus x. That's what h prime of x is equal to. You probably get a point just for that. You want to see if it's undefined or not, right? Is h prime undefined? Well, they tell you g is differentiable, okay, that means that its derivative is going to exist everywhere, okay? So we know the derivative is continuous, it exists right here. And we know y equals x, this function is just a linear, it exists. So this right here exists for all x. Exists for all x on, what was it, -7 to 5. Okay, so really you don't need to worry about h prime being non-existent. That's what it comes down to. But you do want to set it equal to 0. And here's where things get weird, because people are like, how the heck am I supposed to solve this? Because I don't know what the heck g prime of x is. You know, it's actually a lot of different functions, right? So piecewise up here. Remember, if you subtract two things and they're equal to 0, I think yesterday's lesson, we subtracted two rates of change. We had the two rates of change being equal to each other. I think it was entrance rate equal to exit rate. Then we subtracted them. Got w of t minus r of t is equal to 0. Here it's the opposite. We have two things being subtracted equal to 0. That means the two things are equal. So if you want to know when h prime is equal to 0, you're really looking for where x is equal to g prime of x, okay? And people are like, what the heck are you talking about? But this is a function x. That's just the function y equals x, right? Like this is just the function y equals g prime of x. We have y equals g prime of x. It's right here. If you want to know when two functions are equal on a graph, you want to see where they, very good, intersect. So we're going to graph y equals x on this graph right here. Just be careful. It's got to pass through the point 3, 3, which is here. So that's the place where they intersect. It also has to pass through 1, 1. 2, 2 is somewhere in between. We know 2 is right there, right? So 2, 2 be right here. So here, right here, that's my line y equals x, right? You can actually see there's two places, this guy will keep going, on the interval from -7 to 5 where x is equal to g prime of x. Okay, this spot and this spot. You don't know what this spot is right here, and you could try to guesstimate, but it's not one of those easy guesstimations. Like if you guess 1.5, you're wrong, but you could do that right now if you wanted to. You could even say like a right here, because maybe you don't know what the value is. You know, but this thing right here is true. We'll say when x equals, so I know it's true when x is equal to 3, and also when x equals a. Because maybe you don't know what a is equal to. Getting a is the hardest part of this problem right here. Maybe you ignore that. You're not going to get full points, okay? But right now, you want to know if there's a relative min, a relative max, or neither. And that's really, you know, that's where I draw the line, okay? You know, the g prime of x minus x line going from -7 up to 5. I got two critical x values, right? I have a, which we know is going to be somewhere in between here. Oh, I called it a over here for a y value. That's silly, right? That's the y value. But I don't care about the y value. I actually care about the x value down here. So my apologies. That's what a is right there. The y value might come into play as well. I don't think it does actually. Do they want to know? If they wanted to know like what the local max was or what the minimum was, then you need to know about the y value. But I just care about that x value of a right there. Okay, I'm going to call him a. So I know a is, you know, less than 3. So 3 is the other one right here. Then you can just really think about it. You know, if g prime of x minus x, you want to know if it's positive or negative. Well, from -7 to a, you can see that g prime is always greater than x, okay? And if g prime of x is greater than x, that means that when you subtract the x from g prime of x, you're going to get a positive back. You can even use a number. Plug in like a 0 here. G prime of 0 is 2. And if you plug a 0 into x, you get 0 back. So 2 minus 0 would be positive. You could do it that way. Just like between a and 3, you could plug in the 2, right? And here you can see a 2, g prime of 2 is 0, but if you plug 2 into y equals x, you get 2, okay? So we can see here that 0 minus 2 would actually be a negative. Or just look anywhere between a and 3. You can see anywhere between a and 3, y equals x is greater than g prime of x. Just like from 3 to 5, anywhere from 3 to 5, you can see y equals x is also greater than g prime of x. Plug in a 4 if you want. G prime of 4 is, it looks like a 1, right? And if you plug 4 into y equals x, you get a 4 back. So 1 minus 4 would be negative. Again, that means that at x equals a, that's a place where the slope of this function h changes from positive to negative. So h has a local maximum. At 3, though, it has neither, because the slope goes from negative to negative, goes from decreasing to decreasing. So classify each point. So we know at x equals a, h has a local max. Because, and we know the reason why, okay, it's because g prime of x minus x. G prime of x minus x, we know, equals 0. We already said it equals 0 over here. You don't need to see it again. But it's nice to actually roll it in. And changes from, what is it, positive to negative. And then as far as what's going on at 3, at x equals 3, say h has neither. H has neither because, and that's because, you know, g double prime on minus x doesn't change sign, okay? We know that g prime, pardon me, of x minus x equals 0, but doesn't change sign. It doesn't change sign. Now that right there, those justifications that showed, this one we've seen 100 times, but something like this showed up in an implicit differentiation problem we did. I don't know if it was last week or a couple weeks ago, whenever it was, I can't remember. We're going to do more of that because that's something that might definitely show up on your AP. It's on AP Classroom. So more on that Thursday and Friday. By the way, this is enough for 8 out of 9 points. You know, why aren't we getting 9 out of 9? We never said what A was equal to. So if you actually want to know what A is, it's kind of tough here to find this x value of A, because that's where x is equal to g prime of x. But g prime of x looks like this on the interval, okay? And you actually need to come up with what the function is. You got to solve, you know, because if you want to know when g prime of x equals x, well, we need to know the actual, you know, what g prime of x is equal to here. And it's not really the worst thing in the world. It's a circle, okay? Believe it or not. Okay, you could think about a circle with center at the origin, a radius of 2. That's x squared plus y squared equals 2 squared. So really x squared plus y squared equals 4. That's this circle right here. You want to solve for y. So y equals 4 minus x squared. Y squared equals 4 minus x squared, right? Subtract x squared from both sides. Thus, y is equal to, there is 2 square roots. Okay, because you need to worry about positive square root, negative square root. But this is the positive square root. It represents this semicircle here. The negative square root represents this semicircle. So actually what this function is equal to is the square root of the quantity 4 minus x squared. And this is what you need to solve, set up and solve to get what value of A is equal to. And you might be like, what the heck is going on right now? That's why it's so difficult. And like I said, that's why I skipped it. You know, I did this and I kind of got away from it because this is going to take a lot of time. It's doable here. Square both sides. We get 4 minus x squared equals x squared. If we square both sides, add x squared to both sides. 4 equals 2x squared. So 2 equals x squared. So radical 2 is equal to x. Thus, A equals radical 2. So now they have that value for all the other stuff that you wrote down here. Once again, I wouldn't worry about that, okay? It's some really filthy stuff right there. And 3, you could just do by the graph, okay? That's obvious right there. So do the best you can. At least if you do the 3 right here, you could pick up a point. That could be your 6 point right there. Filthy problem. Remember, that's what we're doing right now. We're doing some filthy problems because that's where you're going to see on your advanced placement exam, okay? Filthy problems, you're not going to be able to do every part. In fact, they said that they're purposely going to set it up so you're not able to finish every part, you know, like 99% of people. So do the parts that you can, then go back and use that extra time to do the best you can to earn some points. Let's dive into a 2007 problem here. No calculator. This one involves some cool table stuff. Integrate the rate isn't really on here, but there's some related rates on here. I'm willing to bet some money a related rate's going to show up as a little part of one of your part 2 problems. But anyway, let's have some funny. The volume of a sphere, let's have some funny. Let's have some fun. The volume of a spherical hot air balloon expands as air inside the balloon is heated. Oh, it's a party now. The radius of the balloon in feet is modeled by a twice differentiable function. We know that's important, right? R of time t, where t is measured in minutes. And that gives us the actual radius in feet, right? Then they say from 0 to 12 minutes. They tell you the graph of R is concave down. You know, why would they tell you that? Who knows? There's 100 different reasons. But they don't give you info about R, because in the table, they don't give you R. They give you the rate at which R changes. Okay? And remember, R represents the radius of the balloon. R prime of t, that's the length of the radius of the balloon. That's what R represents. R prime of t represents the rate of change of the radius of the balloon. So think about it. If you integrate the rate at which the radius of the balloon changes, you'll actually get the change in the radius of the balloon. The radius of the balloon is 30 feet when t equals 5. So it's actually an initial condition. Then they give you a volume formula of the sphere for some reason. So just be careful. They talk about this function R that represents radius of a balloon, but they give you information about the rate of change of that function. So let's dive into part A. Estimate the radius of the balloon when t is equal to 5.4 using the tangent line approximation at t equals 5. Is your estimate greater than or less than the true value? So you want to estimate the radius of the balloon. The radius is R of t, right? at t equals 5.4. So you want to approximate r of 5.4, but they tell you to use the tangent line approximation at t equals 5. This is local linearity, okay? We don't have r. That's why we're going to estimate it here. We're going to estimate it using the tangent line approximation at t equals 5, because at t equals 5, as long as you have a t value very close to 5, it's going to represent the tangent line at t equals 5 is going to kind of represent the radius of the balloon, as long as it's at a time that's really close to t equals 5. And here, t equals 5.4, pretty close to t equals 5. Even if you don't get that, they say using the tangent line approximation. They don't say of what function, because they want you to estimate the radius. So you need to know the original function is r of t here. Not the easiest thing. They don't really spell it out for you. But that means if you want the tangent line, first we get the slope. That means you want to take the derivative of r of t and plug in a 5 right there. So you want r prime of 5. And believe it or not, that's right here in the chart. R prime of 5 is actually equal to 2, okay? So 2 feet per minute. You don't really got to write the units down right there. You know, second, we want to get what y is equal to, what b is equal to. That's when we plug into y equals mx plus b, replace everything but the b. We know m is 2, right? That's the slope you're all looking for. We just got that. X is t, right? You know, t equal to 5 right here. And then we want to plug back into the original. That's r of 5, which they actually told us was equal to 30. That's up here, okay? The radius is going to be 30 when r is 5. That means r of 5 is 30. It's actually the initial condition. Okay, and then we can see here that we actually have 30 equals 10 plus b, so that was that 20 equal to b. So therefore, the tangent line approximation, really, y equals 2x plus 20. All right, you know, technically what's going on with that is it's not really 2x plus 20, right? Really, it's r equals 2t plus 20. You could probably get away with writing it this way, because the next thing you do is you're going to approximate r of 5.4, so approximately, and now it doesn't matter, right? Because it's 2 times 5.4 plus 20. I'm even going to leave it that way, okay? No calculator. You know, right now, maybe you can, I don't know, can we read this? Doesn't that look like, is that a 2? Is that even a 5.4? Is that a 70? Is that a 20? You know, be careful when you write these things out. Make sure that it's legible, okay? So here I'm going to say, once again, 2 times 5.4 plus 20. I think that's a little bit better than what I had written before, okay? So be careful with stuff like that. Also, that's the tangent line approximation. Now you need to know if the estimate is greater than or less than the true value. Remember, a tangent line approximation is going to be greater than the true value if the function's concave down. Because if the function's concave down, the tangent line is always be above it. But if the function's concave up, the tangent line will always be below. Then it's going to be less than the true value. It's going to be an underestimate. Underestimate for concave up, overestimate for concave down. They tell you the concavity of r. They tell you r is concave down. So that means that this right here is going to be an overestimate greater than the true value. This is greater than the true value, because, and it's because r is so concave down, which they told you. So the tangent line would actually lie above, okay? Because you see anything I wrote? This is greater than the true value because r is concave down. You just had to take home, it dealt with, I think it was differential equation, okay? I think it was the one with the potato in the oven. Tough problem, by the way. And they want to know if it was an underestimate or overestimate. And a lot of people told me it was an underestimate because the function was concave up. The problem was you didn't know the function was, you knew the function was concave up because the second derivative was positive. Too many people, what was the function? I think it was g. Was it g? Was it w? I don't know with the potato. Let's say it was g, but that might have been the function they used to model it in part C. I think it was. So I think it was w. So a lot of people said because, you know, w is concave up, but you really need to say because d squared w over dt squared is greater than 0. You knew it was concave up because the second derivative was positive. Here you know r is concave down because they told you r is concave down. So be careful. Maybe you figured out r is concave down because r double prime was negative. That should be the reason then. If they said, you know, maybe they gave you a chart for r double prime, you realized it was negative. So be careful. Always justify in terms of the information that they give you. If you're going to make a leap from one piece of information to another piece of information, show that leap, okay? They want to actually see that right there. Part B, find the rate of change of the volume of the balloon with respect to time when t equals 5, indicate units of measure. So the reason this is a hard problem is because things are hidden in here. Just like local linearity was kind of hidden here. I don't think it's so bad in part A. Part B, the rate of change of the volume with respect to time. They don't tell us volume, and we could say it's v prime of t, but really, I'll say dv over t, because think about it. They want a rate at a specific instant. We want dv over dt, want dv over dt when t equals 5. And you might be like, where's this v coming from? Well, they gave you the formula for the volume of a sphere. Volume equals 4/3 pi r cubed. So really right here, this is really related rates in disguise. So we know we can get dv over dt by taking the derivative of both sides implicitly with respect to t. Drop the 3 down. 3 times 4/3 is 4. Rewrite that pi, raise r to the 1 less. Don't forget to multiply by dr over dt. And that's the dv over dt that I want. The problem is, I'm now looking at one specific instant. One specific instant is this. Well, it's the specific instant when 4 pi is 4 pi, because 4 pi is 4 pi at any given instant. But I need to know what r is at this instant. And I need to know what dr over dt is at this instant. Believe it or not, I know what r is at t equals 5. They straight up told me when t equals 5, the radius is 30. So when t equals 5, that means that r is equal to 30. So I know this is actually going to be 30 right here. You know, the problem is, they're like, what's dr over dt, right? You know, remember, dr over dt, that's just the same thing as r prime of t, right? Just like dv over dt, it's the same thing as v prime of t. So you really just want r prime of t evaluated at t equals 5. So it's really just r prime of 5, which is in the chart, okay? It's actually equal, r prime of 5, just equal to 2. Okay, so it's not as bad as it might seem, but it is tricky, okay? Don't get me wrong. You don't need to simplify, but you got to make sure you have your units right there. R prime is in feet per minute. That's dr over dt is in feet per minute. But dv over dt is a volume changing with respect to time. That's going to be cubic feet per minute, because volume is in cubic feet. If it was a surface area, then it would be in square feet per minute. Don't flub up those units, okay? You're going to lose points right there. This comes out to, you don't have a calculator, so there's no way you're simplifying it. It's actually not bad to simplify, but 7,200 cubic feet per minute, but it's not necessary. I'd stick it to the squirrels and leave it like that right there. So it's not that B is hard. It's just that it's like hidden, and that's the way related rates are going to be. They're going to be kind of hidden inside these problems. We'll do more and more. I really think one's going to show up on your AP. Part C, similar to something we did yesterday. We've been talking about trapezoidal sums by using the intervals indicated by the data in the table. Yesterday, we did a left sum with the indicated by the data in the table. Now we're going to do right sum with the data indicated by the data in the table. We'll eventually do ones where, you know, it's subintervals of equal length as well, so you could just do the expansion. But the good thing is even the subintervals are equal length, you could still do what we're about to do. So use the right Riemann sum with the 5 subintervals indicated by the data in the table. So 1, 2, 3, 4, 5 right there, those 5 sub-intervals to approximate this integral. And then using correct units, you want to explain the meaning of the integral, okay? So the integral 0 to 12 of r prime of t with respect to t. If they were subintervals of equal length, we'd be getting delta t right now, but we're not going to do that. We're just going to calculate the area of each rectangle separately. Remember, the first rectangle goes from 0 to 2, right? So we know that his base is 2. So that's my delta t. It's a different delta t for each rectangle here. And since it's a right Riemann sum, you want to plug in the 2 for the height. So r prime of 2. I really want to do that 5 times. Plus the next one goes from 2 to 5, so a base of 3. Since it's a right sum, let's plug in the 5. So r prime of 5. Plus next one is going to go from 5 to 7, so a base of 2. I'll plug in the 7 since it's a right Riemann sum, r prime of 7. Plus now we're going to go from 7 to 11, that's 4, r prime of 11. And then finally from 11 to 12, that's only 1, and then r prime of 12. Okay, and once again, show that you know how to plug the numbers in here. This is really 2 times r prime of 2, which is 4, plus 3 times r prime of 5, which is 2. We've used that a bunch of times already, this problem. Plus 2 times r prime of 7 is 1.2. Let's make sure that 2 is legible right there. Plus 4 times r prime of 11 is 0.6. Remember dates Mr. Pushy has this weekend. Plus, you know, they show up to dinner and then she sees him and runs out. Plus 1 times r prime of 12.5. And that's what I'm going to leave. Okay, so I'd set it up that way. Stick it to the squirrels once again. So, you know, it shouldn't be too terrible to set that up. Okay, we've done that before. They want to see the expansion and they want to see this piece right here. Now we want to explain this meaning. So remember, the second you want to explain a definite integral, we always start with the change in. The change in. Just like if they want you to describe a derivative, we start with rate of change of. If you want to describe, an integral, you start with the change in. And remember, what do we just integrate? We just integrated the rate of change of the radius of the balloon. And if you integrate the rate at which the radius of the balloon changes, you actually get the change in the radius of the balloon. So the change in the radius of the balloon, remember, it's the actual change in the radius. So it's going to tell you how much the radius changed by. It's not a rate, okay? If you integrate feet per minute, you can look at it this way. If you integrate feet per minute, that's r prime of t is in feet per minute. With respect to minutes, remember, you multiply. You're getting an area here, right? Height times base. And when you multiply here, you're just left with feet. That's why you're in feet, okay? It's just the change in the radius. But don't forget the units and the bounds from t equals 0 to t equals 12 minutes, okay? So it's really something that we talked about before. If you have an applied problem, which I really think you're going to have on your AP, I think one problem will be applied, one will be abstract. I think they're going to get a table thing like this going on. It's been very popular. They might want you to approximate r double prime of 3, do r prime of 5 minus r prime of 2 over 5 minus 2, stuff like that, okay? We did some other table problems. I want you to be prepared for that. Part D is where things get wonky. It's only worth 1 point, okay? So a lot of people aren't even going to be able to do it, but let's play. Is your approximation of part C greater than or less than the true integral right here, given reason for your answer? We talked about it yesterday, okay? If you do a left or a right Riemann sum, you want to think about whether a function is increasing or decreasing to know if it's an over approximation or an under approximation. The problem is, r prime right here, they don't tell you whether or not it's increasing or decreasing. And, if you look at the chart right here, a lot of people are going to say that it's decreasing, okay? But the problem is you don't really know what's happening in between. This is where it's really tricky. They did tell you that r is concave down, right? Do you remember that? So if r is concave down, that means r double prime is negative, right? Because r is honk down. If r double prime is negative, r double prime is the rate of change of r prime, right? Rate of change of r prime. So if the rate of change of r prime is negative, that means that r prime is going to be decreasing. We're going to say, so r prime is decreasing. Not so easy to see. It looks like r prime is decreasing, but it's not enough here because they don't tell you when it's equal to 0. It could be increasing and decreasing in between. But if the graph of r is concave down, that means that r double prime is always negative, which means that r prime, the slope of r prime is negative. That means r prime is decreasing. And think about it. We just did, r prime is decreasing, so draw some decreasing function. Who cares what it looks like? Doesn't matter about concavity. Concavity matters when you over approximate or under approximate a trapezoidal sum. Riemann sum, left or right, you worry about increasing and decreasing. So if you do, I'll even do this. Let's do 2 rectangles. People get all annoyed. They're like, well, it's supposed to be 5 rectangles. It doesn't matter. The less you do, the easier it is to see if it's an over approximation or an under approximation. And this is what, a right Riemann sum. So here, if you plug in this rightmost value for rectangle 1, this is the height, draw a horizontal line. Rectangle 2, plug in the rightmost value, horizontal line. You could see this is an under approximation, okay? So this right here, our approximation, that we got right there, is going to be an under approximation of the true value, okay? So we could say, so under approximation, because, and we know it's really because r prime is decreasing. Which is where it gets sloppy, I get it. But there are 2 types of, under approximation, over approximation things they ask you about on the AP. One is this, okay, Riemann sums or trapezoidal sums. Riemann sums, under approximate, over approximate, worry about when a function's increasing or decreasing. Trapezoidal sums, over approximate, under approximate, worry about if a function's concave down or concave up. If it's concave up, trapezoidal sum will over approximate. Concave down, trapezoidal sum will under approximate. The other type of approximation is the linear approximation, right? With local linearity. Then you need to know if the graph is concave up or concave down. So these are the 2 types of approximations that I think you might see on your AP. This one right here, definite possibility. It shows up a lot less often than this one. So this one I really think is going to be on there somewhere. It might not be. This one right here, showing up on a couple of the practice problems, though, that they've given out. So it's a definite possibility. Anyway, so that's Wednesday's lesson. Okay, so like I said, Thursday and Friday. Tomorrow we'll get into some cool second derivative stuff. We've done a couple problems like it, but they've also released some. And we'll talk about an accumulation function. Friday we'll get some differential equations going again, because I really think one of your problems is going to be a differential equation problem, because there's so many different things they could do with it. We'll do that on Friday. We'll do some more accumulation function. Then on Monday, I don't know what we'll focus on yet. I haven't planned that far, but, you know, the day before the AP, we're going to do the best we can, and I'll get some review stuff for you guys over the weekend as well. So, Berto signing off. Love you all. I hope you're staying happy and safe, and we'll talk to you later. Adios.